For our next example of a ring, we're going to look at the ring of 2 by 2 matrices with real number coefficients. So this was denoted M subscript 2R, and it was the set of all matrices A, B, C, D that were 2 by 2, where the entries, the A and the B and the C and the D, are real numbers. All right, so we already knew that it was a group under addition. So numbers 1 through 3 above in that definition of a ring hold. So now we're left checking the rest of them. So number 4 is another additive property. This is addition is commutative, right? So if we want to check this, we're going to think what it means to add two matrices. So A, B, C, D plus E, F, G, H. What do we get? We get A plus E, B plus F, C plus E, D plus H. And if I instead add in the other order, E, F, G, H plus A, B, C, D, what I get here is E plus A, and F plus B, and G plus C, and H plus D, right? And because addition is commutative in R, that means these matrices are the same, right? Each entry, like if we look at that top left entry, A plus E versus E plus A, well, those are the same because when we're adding real numbers, it's commutative. All right, so number 4 holds. We're fine with number 4. Okay. Now we need to talk about the rest of them. So property 5 was a multiplicative property. It was multiplication is associative. So before we can really do that, we need to know how to multiply matrices. We haven't talked about that yet. If you know how to multiply matrices, you can sort of zoom through this next bit. But otherwise, I'm going to walk you through how to multiply matrices because it's a weird process. And if you haven't seen it before, or if it's been a long time, you might need some refreshing here. All right, so if I want to multiply these two matrices, A, B, C, D times E, F, G, H, what we're going to multiply is a dot product of rows of the first matrix with columns of the second matrix. So I'm going to take, for my answer here, I am going to take the first row, A, B, C, D, I'm sorry, A, B, and the first column, E, G, and I'm going to do their dot product. So the dot product is you multiply the corresponding entries, so A times E, and add the B times G, the corresponding second entries, like that. All right, if I want to do this entry right here, the first row, second column entry of my product, I'm going to do the first row, second column of my two matrices. So I get A, F plus B, H. Okay. If I want to do this entry, so that's the second row, first column, I'm going to do the second row, first column dot product. So I get a C, E plus D, G. And then let's do blue. And then for this last entry, second row, second column, I'm going to do the dot product, second row, second column. So I get a C, F plus D, H. And that's my product of two matrices. All right, so let's now go through the rest of the pieces of the definition of a ring. So property 5 from the ring definition was that multiplication is supposed to be associative. And so I'm not going to go through this. Checking this is just takes a bunch of computation, just crunching things through. But I'm going to set it up so you can see what you would do, and then you should try it. So for the associative, I'm going to take my first matrix, A, B, C, D, and I'm going to multiply it by a product of two matrices. So E, F, G, H, and I, J, K, L. Okay, and so all of those A through L's are just real numbers, and I'm doing this product out. So what I would do here is do the product inside first, and then I'm going to do another step of multiply whatever that product is that turns out to be the EFGH times IJKL, then times the ABCD, and I see what I get. Okay, and then I try this again, but associating, doing the first two ABCD times EFGH first, and then IJKL. So notice we haven't changed the order of the matrices, we're just changing which two I do first. And so if I wanted to check this one, I'd do that inside product first and see what I got. And then IJKL, I'd multiply that by IJKL. Okay? And then I do that next product out and see what I get. And in the end, these will match. As long as you're careful, it all through correctly, these will match. And so this property holds. Number 5, matrix multiplication is associative. Okay. Number 6. So number 6, let me switch back to black here. Number 6 was there had to be an additive identity. And so for 2 by 2 matrices, our additive identity is called I subscript 2. So I for identity and 2, sorry, this is a multiplicative identity. I think I said that wrong. So I for identity and subscript 2 because it's the 2 by 2 identity. So in general, identity matrices look like this. They have ones along that diagonal that goes from the top left to the bottom right. It's often called the main diagonal of a matrix. And there are zeros everywhere else. So for a 2 by 2, we get this 1, 0, 0, 1 matrix. And now what we need to check is that if I multiply any matrix times this identity, what do I get? And if I do it in the opposite order, what do I get? And you should work through these two on your own, make sure it makes sense, but what we're going to get is just A, B, C, D in each case. And so property 6 holds. That's our multiplicative identity here. All right, and then property 7, our last one, was the distributive property. And so again, this is one where we're not going to do the computation out, but I'm going to set it up so you can see what you would do, and then you should try it. So here it's going to look similar to the associative property, but we're mixing our operations. So this time we're going to do ABCD times a sum, EFGH and IJKL. Okay, so this is different than the associative property in this first step because inside we've got that sum, right, of two matrices. And so you're going to do this by, like before, do what's inside those square brackets first, and then do out the product and see what you get. And then we're going to try the other side of the distributive property. We're going to try if I had distributed, do I get the same thing? So if I had done ABCD times EFGH and add to that ABCD times IJKL, what do I get and is it the same? And so here you're going to be doing those products first, right? You're going to multiply those products first and then add them and see what you get. Okay, and in the end, again, these should be the same. And so matrix multiplication distributes over addition. All right, now we have one big warning with matrix multiplication. So matrix multiplication does not satisfy something we're used to. So matrix multiplication is not commutative. Okay. And oops, we can see this pretty easily if we go back and look at our A, B, C, D times E, F, G, H and figure out what that is versus if I did E, F, G, H times A, B, C, D. So if I do the E, F, G, H times A, B, C, D thing, I get EA plus FC as my top left entry. That's first row, first column. And then my next entry, first row column, I get EB plus FD. And then I get a GA plus HC and a GB plus HD. And if we look at what we did in the first place, I'm just going to jot it down real quick. And CF plus DH. So if we compare these two things, they're not the same, right? At first we see, oh, AE, that's the same as EA, but look at that G and FC. There's no reason that those two things have to be the same. They might be. There might be choices of those numbers make these matrices match, but they're not always going to match. So these are not always equal. Okay, so matrix multiplication is not commutative. The order that you multiply matrices in is very important. And so because of this, we notice that in the definition of ring, we did not demand any kind of commutativity of multiplication. When we do have that, it's a very special thing. And so we have this new definition we haven't seen before. If we have a group where the binary operation is commutative, it's called an abelian group. So for addition, this means A plus B equals B plus A. For multiplication, this would mean A times B is B times A. So if we have a commutative operation, it's called an abelian group. A ring is an abelian group under addition. That's part of our definition. That was ring definition part 4. But if we have a ring where the multiplication is also commutative, it's called a commutative ring. So as an example, like R is a commutative ring because the multiplication is commutative in R, but M, oops, to R is not. So this is not a commutative ring. All right, that's it for this video. We'll see another example in the next one.